Hello everyone, this is Yao Li from class Introduction to Engineering System. In today's presentation, I will introduce my final report for the system engineering case study. In this presentation, I choose the National Polar Orbiting Operational Environmental Satellite System as the case study model. First, this presentation will focus on the NASA past analysis and research of environmental satellite systems, following with the description of the endpoint's earlier conceptual phases to validate that there is a real need for the endpoint system. And later, this presentation will explore the potential performances is required for the endpoint system to accomplish its perceived missions. Through the concept definition phase, this presentation will give a more clear picture of this system containing its key characteristics that would achieve the most beneficial balance between capability, operational life, and the cost. Then the detailed engineering design and the process of integrating and the engineering components will be discussed in the engineering design phase and the integration and the evaluation phase. So here is the table of the contents. And during the operation and support phase, a proper operational plan of the endpoint system will be talking about. At last, the challenge section and the summary section illustrate the problems throughout the development of the whole endpoint system and what I have learned from this case study project. Now let's start with the background part. So what exactly the endpoint system is? The endpoint system is a National Polar Orbiting Operational Environmental Satellite System. It's a satellite system which can monitor Earth, land, ocean, and the atmosphere, including the troposphere and the near space boundaries, to provide data and imagery for weather forecasters, academics, government agencies, and militaries. The goal of the endpoint system is to improve the national space-based remote sensing capabilities for environmental monitoring and global change assessment. So this is just a review part, because we also talking about this part, the background part, and the concept design part in the middle term report. So it's just a review. So for the history of the environmental satellite system, why do we need to care about this? Because the system engineering process which are used in today's complex power project has matured based on well-founded principles and heuristics from past development. Therefore, before going into the concept development stage of the endpoint system, we must first review the background and past analysis of engineered systems for environmental satellite programs. Here, I just list 3 examples, so we can learn something from that. The first one is Vanguard 2. On February 17th, 1959, the first weather satellite, Vanguard 2, was launched. It was designed to measure cloud cover and resistance, but this system fails to evaluate requirements and specifications for the effectiveness before beginning the program. Its poor axis of rotation make it be incapable of collecting a significant number of useful data. And the second example is TIROS. In the earlier life cycle of TEROS program, system engineers develop an effective system concept and architecture. The TEROS concept formulation was strict and very traceable to user needs. The last one is the TRMM. The TRMM program began to relay wind information near the ocean's surface, starting with microwave imagery which resembled radar displays, which importantly improved diagnosis of tropical cyclone strength and location during the 2000s and 2010s. So the TRMM program was structured to address risks in several ways throughout the multi-phase program, where key risks were known upfront. The contractor and the government utilize a classic risk management approach to identify and analyze risk, and then developed and tracked mitigation actions. Identified technical risks were addressed at a weekly chief engineer meeting and often tracked by technical performance measures. The program office, serving in the clear role of integration, were issued a request for proposal to serve bidders for developing concept and made designs. By learning about environmental satellite systems, it can help us in exploring of both successful and unsuccessful methodologies, processes, principles, tools, and decision materials to assess the outcomes of any changeable element at the system level of the endpoint system. So, do we really need a endpoint system like this? The answer is yes. So why? I will analyze this in the first stage of the concept development stage is the needs analysis. Since the last century, environmental satellites have been applied widely in the operations of both military and civilians agencies. Those satellites provide the information used for weather forecasting, monitoring long-term trends in climate conditions, planning for military operations and disaster reliefs, as well as monitoring near-Earth spaceful conditions that affect satellite operations. The United States government realized the huge impact brought by the environmental satellite programs. They invest almost $10 to $20 billion about in those kind of program every year, and this positive financial environment allows a number of military and military programs are now in operation. However, those satellites will reach the end of their useful life in space over the next few years. Based on the design life theory, every satellite program is designed and built to operate for a certain minimum period named the design life. Satellite replacement schedules are typically based on a quantity called the mean mission duration, which combines both the design life of the satellite and the likelihood that the satellite will fail for other reasons. Once the Department of Defense, the National Oceanic and Atmospheric Administration, that's NOAA, and NASA found that their satellite systems are reaching the end of their operational lives and stopping to function at some level, they can launch new satellite systems to replace the old ones. To avoid the discontinuities of the system replacement, those three agencies need to store several more satellite systems awaiting launch, meanwhile incubate new programs for the future. So in this case, the endpoints program, which is the next generation operational United States polar orbiting environmental satellite system, replacing the current generation polar operational environmental satellite, managed by the Department of Commerce, National Oceanic and Atmospheric Administration (NOAA) and the Defense Meteorological Satellite Program, known as DMSP, managed by the Department of DoD, needs to be developed for meeting the military weather forecasting, storm tracking, and climate monitoring requirements. So we really need this program. Then let's look at the concept exploration part. The Integrated Program Office, known as IPO, of the Endpoints Program, formed by the Department of Defense (DoD), the NOAA, and the NASA, suggested three options that the whole research team has discussed for designing the initial prototype of the new converged satellite system. Each option is built around a core set. Each option is built around a core set of three types of instrument, including a visual imager, which is used to determine the present and properties of the clouds and the temperature of the Earth's surface, a microwave imager or sounder, which is used primarily to determine the atmospheric humidity and the temperature as a function of altitude, and the space environment sensor, which is used to determine the condition in outer space that affect satellite operations, the operation which are different by the relative capabilities of the instrument site, offer the technical and the economical feasibilities for designing the endpoints system. So let's look at what exactly these three options are. The first option would provide the most capable as well as most expensive satellites, and would integrate or cooperate with upgraded versions of all three instruments. The second option would reduce the cost by replacing the more capable microwave imager and the space environmental sensor instrument. Then the version carried on the current generation of POES and DMSP satellites. And the third option would reduce the cost even further by using the visual imager and the microwave imager or sounder carried on current generation satellites, as can be seen from the table 1. As can be seen from the table 1, option 1 would carry the all upgraded instrument VIIRS, MIS, SEMN. Option 2 would carry the current generation visual instrument AVHR and upgraded microwave and space environmental instrument MIS and SEMN. Option 3 would carry the current generation visual and microwave instrument and upgraded space environment instrument. So the the IPO expected that the satellites in the first option would be capable of measuring about 37 EDRs, including all 6 EDRs that endpoints program has designed as the key performance parameters. Each of the 2 satellites that all this system needs would cost about 1.2 billion to manufacture, and the total program acquisition cost, including supporting data handling, processing, infrastructure systems, engineering, and program management cost, would be about 4.2 billion. If the cost for launch support, satellite storage, and on-orbiting operational through 2037 are included, the total program cost for the first operation would be about $6.1 billion. The satellites for the second option would have less capability, measuring only the 30 EDRs, and including all 6 KPPs, they would cost about 700 million of each satellite to produce. The total program acquisition cost would be about 3.2 billion. And the third option is the most cheapest one, with the lowest cost, and the capabilities would measure the 25 EDRs, only including 4 of the 6 KPPs, and the unit production cost would be about 400 million. The total program acquisition cost would be about 2.7 billion. So the IPOs also explore other possible alternative approaches for designing the earlier model of the endpoints system, which may cost the varying amount of cost. One is, for example, delaying the start of endpoints development to reduce the near-term cost, and another one is fielding sensors on several smaller satellites rather than on a single satellite, or not replacing the POES and DMSP satellites. So this is the part of the concept exploration. We can see the IPOs gave us several options. So let's move on to the concept definition stage. The IPO use the quantity of environmental data records that the satellite could produce, the key performances parameters, the effect of 3 main instruments of a satellite, and the cost of each option plans to compare the capability of the endpoints options and select the preferred one. So what is the EDR? EDR is the environmental data records. When it first received, the satellite data are considered as raw data to make them usable. The processing center format the data so that they are time sequenced and including Earth's location and the calibration information after formatting. These data are called raw data records. The centers further process these raw data records into channel-specific data set called sensor data records and temperature data records. These data records are then used to derived the weather products called environmental data record (EDR). So first, let's look at the EDRs. So the option 1 can produce the 37, and the option 2 can produce the 30s, just the 30s, and the option for the option 3 only can measure 25. So, and between them, the huge problem for the option 3 is cannot contain the other two KPPs that also needed for the endpoint system. So, but the other options, option 1, option 2, can contain those 6 important parameters. So in this case, people usually want to choose the option 1 or option 2. So let's look at what's the next standards for IPOs to choose the preferred options. It's KPPs. So what is KPPs? The key performance parameters is what the important performance goals are in a United States Department of Defense (DoD) acquisition under the Joint Capabilities Integration and Development System process. So as we discussed before, so the option 2 lack of two important KPPs, so it's not possible for the IPOs to choose option 3. Now let's look at with the consideration of all above technical and financial aspects that we have discussed, the IPO initiates a program definitions to define endpoint's total system architecture, including space, ground processing, and command, control, and communication components, as well as to development specifications for sensors, spacecraft integrations. The option 1 concept is applied to let's look at it. The option 1 concept is applied to the space segment design process. The VIRS combined the radiometer accuracy of advanced very high resolution radiometer currently flew on POES with the high spatial resolution of operational line scanned system flew on DMSP. It has 22 channels grouped into the panchromatic day and night band, visible and near infrared, short and mid wave IR, and long wave IR with additional spectral capabilities that can be used to determine ocean color, and the MIS replaced the microwave imager capabilities of Japan's advanced microwave scanning radiometers on NASA's Earth Observing System satellite, and the atmospheric sounding capabilities of the spectral sensor microwave imager or sounder on the remaining series of DMSP satellites. So after the concept has been built, so let's look at the advanced development stage. Because according to our lecture notes, the main purpose of the advanced development phase is the identification and reduction of development risk. In this phase, the Integrated Program Office, the IPO, first evaluated the risk of the endpoints program in three aspects, including technical, schedule, and cost risk for its overall system integration. The launch segment, the space segment, the interface data processing segment, and the command, control, and communication segment. The result of this evaluation shows that the interface data processing segment, the space segment, and the overall system integration had a high risk component. As you can see from this table is the right part. And the table 3, the result of the 1997 risk assessment, as well as the program office estimate risk levels by August 2002, and by first launch, demonstrate the interface data processing segment and the overall system integration were assessed as a high risk in technical, cost, and schedule areas. The space segment was assessed to be high risk in the technical and cost areas, and moderate risk in the schedule areas. The launch segment and the command, control, and communication segment were determined to present low and moderate risks. The program office expected to reduce its high risk component to low and moderate risk by the time the development and the production contract was awarded, and to have all risk levels reduced to low before the first launch. So what kind of actions they take to reduce that risks? There are three kind of actions they are implement. In order to reduce the program risk, the program office designed and implement multiple risk reduction actions. One risk reduction action only target the space segment risk by initiate the development of key sensor technology in advance of the satellite system itself. Because environmental sensors usually need 8 years to be developed, the program office began developing 6 of these 8 sensors with more advanced technology earlier. In the later 1990s, the program office awarded contractor for the development, analysis, simulations, and prototypes fabrication of 5 of these sensors. In addition, the NASA awarded a contract for the earlier development of 1 other sensors. Another major risk reduction action addresses risk in 3 of 4 segments with identified risk is called the endpoints preparatory project, known as NPP. NPP is a planned demonstration satellite to be launched in 2006, several years before the first endpoints satellite launched in 2009. It's scheduled to host 3 of the 4 critical endpoints sensors, like the visual infrared imager, radiometer suite, and the cross-track infrared sounder and the advanced technology microwave sounder, as well as 2 other non-critical sensors. Further, NPP will provide the program office and the processing centers an earlier opportunity to work with the sensor, ground control, and the data processing systems. Moreover, the IPO awarded the contract for the overall program and is monitoring and managing contract deliveries, including products that would be tested on NPPs. The program office is also continued to work on various other risk reduction activities, including learn from experience with sensors on existing platforms, including NASA research satellites, and the endpoint's airborne sounding testbed. So, after talking about the advanced development stage, let's look at the engineering design phase. So during this phase, the detailed engineering design of the endpoint system is performed, and the endpoint's program definition and risk reduction contractors may propose alternative architectures and solutions during this period. However, the main goal of meeting user needs with the most efficient, cost-effective design still remain important. So the endpoints program office also adopt an open system approach to achieve the standardizations. The approach makes the endpoints contractors implement an architecture that defines the internal endpoints interface by standards used by the industry and defined through a careful process, like IEEE gave a standards. In addition, the endpoints will support open system architectures for the DoD, the Department of Defense Joint Technical Architecture document. So the IPO designed 5 segments for the endpoints system, which are the space segment, the command, control, and the communication segment known as C3S. And the next one is interface data processing segment. After that is launch support segment, and the last one is field terminal segment. So for the detailed design, the space segment consists of a satellite that will collect global multispectral data on clouds and other climatological and solar geophysical parameters. The endpoint satellites also carried the advanced data collection system and search and rescue sensors. The satellites stored and transmit all data to ground stations, possibly through data relay satellites, and provide a continuous real-time transmission for receptor of the data by field terminal within the wheels of the satellite. For the C3 segment, this segment consists of shared and dedicated resources. The C3 segment functions including mission management and planning and resource schedule, satellite operations, automatically resolution system security, relays of data to the IDPS network management, and spacecraft and sensor engineering support activities such as launch and earlier orbit checkout. For the interface data processor segment, it consists of ground hardware and software elements which ingest and store the satellite missions data and process them as necessary into raw data record as known as RDRs, sensor data records known as SDR, or temperature data records, and also the EDRs, the environmental data records. These data records will be received by four endpoints centers: the Air Force Weather Agency, the National Environmental Satellite Data and Information Service, the Fleet Numerical and Oceanographic Centers, and the NOAA Oceanographic Office. These centers will process endpoints, product, and other data for achieving and dissemination to their customers. The fourth segment is the launch support segment. The launch support segment provides the resources to accomplish launch operations and to place each satellite into the correct orbit. This segment includes all launch support equipment, including the airspace ground equipment, real property installed equipment, and the launch facilities. The last department is the field terminal segment. This segment will receive the real-time mission data transmitted from the satellite. The endpoint's IPO supplies the field terminals software and hardware which are capable of processing the endpoint's satellite high rate data and low rate data. Those software and hardware enabled the field terminal to process the high rate data and low rate data into EDRs. If the field terminal beyond the software and hardware specification requirements of the main contractor is only provided for completeness of the operational test program. Current field terminal used within the DoD and the DOC may no longer continue to be used throughout the endpoint's life cycle as technology advanced. Field terminal users need to procure new terminals or just upload or update or modify the existing terminals. So, after knowing the details of the design, so let's look at the integration. At this stage, bidding contractors develop a proposal which contains an integrated master plan known as IMP and an integrated master schedules IMS, which outlines the proposed developmental test and evaluation activities. Their proposal described their approach for manufacturing, integration, environmental testing, and acceptance testing. In addition, it's described how they are integrated into the verification and test program. So the integration of the endpoint system consists of combining the mechanical and electrical subsystem elements into a single entity through the application of logical process taking into account the physical and functional aspect of the subsystems interrelationships. The integration of this system is characteristic by three district levels of the effort, which are the project management, integration, the integration of physical systems, and the integration of subsystems combined through the advanced design. The overall coordinator of the endpoints project is responsible of the system program director group, that's SPD group. So it's consisting of a project manager and his staff. This group is assigned the task for the translating functional concept into an operational satellite. And for the integration of a physical system, the actual physical integration of the endpoint system is accomplished through the combined work of a mechanical integration group and a electronic integration group working together in a concert effort. After all of its subsystems have been produced, they are assigned to the mechanical group for installation. The assembling is then transferred to the electronic integration group, where electronic integration process according to the prepared flow chart, which will related to the most effective manners of checking out the subsystems one at a time. The mechanical group is on standby during the electronic integration with no integration duties to perform other than those related to the installation of the electrical interconnected connection system. Moreover, for the last level is the subsystem combination through the advanced electronic design is a more complicated form of the partial satellite integration. Is accomplished through improved circuit design using the most advanced electronic packaging technology. Several system elements are combined into a single, simplified, more reliable package with many functions accomplished internally, thereby simplifying input and output and eliminating removing some several complicated interfaces. And for this part is also for the evaluation after all the subsystems have been integrated into the basic structure. The operation test agencies for the endpoints program conduct a series of tests and evaluate to determine if the system is operationally can meet the requirements as we discussed before. The operational test program consists of operational assessment combined with development testing and operational testing. Some standard like this. And let's move on to the post development stage. In this stage, we need to talking about two aspects. One is production, the other one is operation and support. For the production, according to the lecture notes, no matter how effectively the system design has been engineered for production, problems inevitable arise during the production process. In this section, I will discuss some problems may happen to the electronic devices of the endpoint system. So the first problem is the first difficulty for the production of the space electronics to overcome is the vibration imposed by the launch vehicle. The demands placed on a rocket and its payload during the launch are severe. Rocket launchers generate very large noise and the vibrations. There are literally thousands of things that can go wrong and result in a ball of flame. When a satellite separated from the rocket in space, large shocks all happened in the satellite's body structure. Pyrotechnic shock is the dynamic structure shock that occurs when an explosion happened on a structure. So the pyroshock is the response of the structure to high frequency, high magnitude stress wave that will create through the structure as a result of an explosive charge, like the ones used in a satellite injection or the separation of two stages of a multi-stage rocket. So the next thing is outgassing. It's another major concern for the production of space electronics. Plastics, glues, and adhesive can do outgas. Wipers coming off the plastic devices can deposit materials on optical devices, thereby degrading their performances. For example, an automobile plastic dashboard can emit a wiper that deposits a film on the windshield. So this is a practical. This is very a real things we can see. So use ceramic rather than plastic components can delay this problem in the electrical devices. And the last thing I want to talk about is the high level of contaminations on surface that can contribute to electrical discharge. Satellites are vulnerable to charging and discharging. For that reason, space applications requires components with no floating metal. Satellite charging is a variation in the electrical potential of a satellite with respect to the surrounding low density plasma around the satellite. The extent of the charging depends on the design of the satellite and the orbit. So these are the problems we need to concern about. For the operation and support phase, the IPO established a mission control center, which is comprised of two main control rooms, one for ground missions and the other is for the low Earth orbit missions. It provides the necessary monitoring and the control of all operational satellites and the associated ground infrastructure. It also ensures the continual communications with and the data acquisition from satellites through a network for a primary and backup ground stations distributed around the United States. Teams of satellite and ground segment controllers work around the clock, supported by the teams of on-call operators and maintenance engineers. So the spacecraft commanding is highly automated. The endpoint satellite system use a mission planning system in conjunction with a flight dynamic system to produce a weekly automatic schedule. This schedule is used to send automated procedures to both the spacecraft and the ground facilities, verify of successful completion of the procedure come back to the monitoring and controlling system in spacecraft and the ground facilities. And the health of the spacecraft is also monitored by the same system. So the IPO also designed a backup control center to ensure the satellite's safety in the event of major problems with the endpoint satellite or communication loss between the satellite and the ground station. So what kind of challenges during this program we encountered? The first two we have discussed in the middle-term report. The first one is the cooperations between separate agencies of different size with divergent objectives and different acquisitions procedure. The example is the partners not meeting the NASA partners not meeting the commitment with planned funding levels and established schedules. So it's usually the schedule will be delayed and the funding will overcharged. The next challenge is the efficiency of the multiple levels of management. Sometimes the one subcontractor make some problems, but the up level, the primary contractors cannot realize that when they realize it is too late to make some adjustment or make some or correct their behaviors is too late, so it's also cost some money. So for the last challenge is the newest challenge when I just explore the final report. So the last one is the programmatic and technical risk that affect and successful and timely deployment of the system, especially changing funding streams and reversed schedules have delayed and expected launch date of the first endpoint satellite and concerned with the development of key sensors and the data processing system cause additionally delayed in the satellite launch date. This planned and potential scheduled delays further affect the continuity of weather data. So for the last part is the summary and the lessons I learned from this project. Through the case study of the endpoint system, I know that the system engineering process transforms an operational needs into a system or several systems of system elements. Architectural elements of the system are allocated and translated into details design requires by the systems engineering process. The systems engineering process for the identification of the needs to the development and the utilization of the product must continue integrated and balanced to balance the requirement, the cost, and the schedule that provide an operational effective system throughout its life cycle. Although the life design procedure of the endpoint system contains the concept development stage, the engineering development stage, and the post-development stage, it still ignores some essential system engineering steps. Despite the huge number of evidence of serious problems as the development of visual interfered imager suite processed, the program execute community did not effectively challenge the IPO's assessment that the problems would not delay the first endpoint launch or access the program's management reserve. Incorrect oversight, in fact, postponed the critical evaluation and the decisions needed to replan the program's faltering elements and contains the cost and the schedule overruns. So therefore, a lot of number of design testing and developmental feedbacks gave rise to create a proven valid system that can be presented as a visible option for production. So thank you. This is my final report presentation.